Welcome back. In section 3.2, we'll be defining and studying eigenvectors and eigenspaces of linear operators. Our goal is to define and study eigenvalues and eigenspaces for linear operators on a general vector space. So far, we've defined eigenvalues and eigenspaces on matrices, so really on linear transformation from Rn to Rn. We can extend these notions to linear operator on a general vector space as follows. So I'm going to take a linear operator from V to V, and V is just any vector space. It could be infinite dimensional, but that's going to be harder to study. So the definition works. It's just that a lot of our tools to compute for computing them wouldn't. All right, so let V be a non-zero element of V. V is called an eigenvector of T if T of V is lambda V for a lambda in R. All right, so this lambda is called an eigenvalue of T, and the eigenspace E lambda of T corresponding to lambda is the space of all vector V in V, so that TV is lambda V. Let's put W, because I've put an assumption here that it's a non-zero vector. Once you define the eigenspace, you allow all eigenvectors plus the zero vector. All right, let's do an example of this. Let C infinity be the vector space of infinitely differentiable functions, and I'm going to take the derivative linear map. So d of f is the derivative of f with regards to x. All right, I want to show that all real numbers a are eigenvalues of d by explicitly finding a a corresponding eigenvector. All right, so I need a function f so that the derivative of f is a times f, where a is some real number. All right, can you think of a function whose derivative has just an extra a in it but otherwise doesn't change? Well, if you want something that doesn't change, you should probably take e to the x, and then to get the a coming out, I'm going to put an extra a here. Then f prime of x is a e to the ax. It is equal to af of x. So yes is an eigenvector with eigenvalue a. All right, that's nice. Now I want to use this to conclude that the space of function from R to R is an infinite dimensional vector space, right? So I want to find inside FR, I want to find a set that's infinite and linearly independent. So what I'm going to do is I'm going to take the set of all of these with A and R. All right, so what I have, this is an infinite set. In fact, it's not even countable, right? It's an uncountable set. So infinite set, and then each element is an eigenvector, but they all have different eigenvalues. By theorem, I mean, we saw it for R, but it actually works. The proof as is works for any vector space. So by theorem 3.3.1, S is linearly independent. And so any vector space that contains S and it has the same operation as the function space would be infinite dimensional. So that means C infinity minus infinity plus infinity is infinitely dimensional. And the same thing for FR, which is even bigger. And if you think of which functions we're using very specific functions, exponentials. Just a set of exponential, that's already infinite dimensional. So you can imagine how big whole functions would be.